Hi, my name is Kris Applegate, and I am going to talk to you a little bit today about big data trends that we've been observing over the last couple of years. This is the summer 2016 update. So we start out with kind of condensing this down to a couple of key themes. First one being an increase in complexity. We're going to talk a little bit about the complication that's more of the advanced data flows, et cetera, have been incorporating. We're going to talk a little bit about the flexibility that you now have with a lot of big data solutions through virtualization, storage, compute disaggregation, big data as a service, and even unified namespaces. We're going to touch a little bit on resiliency, making this a little bit more robust through traditional enterprise means like backup and disaster recovery. We're going to talk a little bit about tiering and some of those concepts, how they can be leveraged now, what type of hardware can be used to particularly enhance that. And then lastly, we're going to cover proposed next generation architecture, kind of for if somebody was going to dive in today, what would it look like if they want to be able to take advantage of a lot of these current technologies. All right, let's go ahead and start. So when way back when we were first starting to see Hadoop was really great at batch analytics and doing things in a very concise manner. Right, what it did really well. As we've started to see it grow, you'll start to see other solutions become embedded and key to the way that Hadoop actually operates. So you see on the left is a traditional illustration of a clickstream traffic analysis where you were generating reports for a reporting server and reading them off with some sort of visualization layer. But Hadoop really did just that, actual hosting of the log files and parsing of that data. Now we start to see things like where Kafka actually sits and acts as a messaging bus, passes off to Flume to ingest both in a what we would call a lambda architecture where you have separate streaming and persistence layers and then a unified layer at the end outputting to a dashboard, right? So the level of complexity has gone up, but Hadoop encompasses a lot more of that complexity, right? It's less and less separate disparate services that you need to actually have in separate clusters for this, separate clusters for that. It's all comes as part of the Hadoop ecosystem, and these roles reside on many of the Hadoop servers that you already have. So a couple of the emerging design patterns, Smack Stack is really popular right now where it uses Cassandra instead of Hadoop as a storage layer. That's a pretty common theme. We use the in-memory data processing that Spark provides, resource management instead of using something like Yarn, which we use in Hadoop. You use Mesos. Akka for something message-driven, kind of a framework or a dev kit. Mentioned the Cassandra storage layer, and then Kafka for distributed message store. We also see things like Lambda. You see me cover that on the previous page where you actually split your persistence in real-time layers, right, and then join them together by a unified query layer at the very end. And then the one on the right, Pancakes, is really, really cutting edge, but it's got a lot of components that you're going to start to see a whole lot over the next couple of years. Presto, a SQL query engine. So really, whether it's Presto or something else, a proper SQL query engine on the front side of your big data solutions is going to become more and more popular. That way you can leverage all those folks that are used to writing traditional SQL queries and statements and all those tools that you've already got developed. It's going to make it one step easier than it previously was through limited functions that you would get through something like Hive. Right? You see Akka here show up again. NiFi, which is a really cool data flow automation framework and GUI. We got Cassandra coming back in again, more workflow management through something called Airflow, another instance of Kafka here, Elasticsearch, right, for indexing in search engines, and then lastly, again, Spark for data processing. So how Dell can help, from here, what components we have available is our certified system for Cloudera Hadoop. Right? That's going to allow you to get started quickly so that you can spend more time working at the data layer and less time worrying about the infrastructure. Right? Dell services can be brought in here to execute a big data workshop where you can actually work with them to plot a course towards where you want to be, start incorporating some of these ideas for more complex designs. And then you can also engage the Dell Customer Solutions Center. Right? Collateral that already exists, so we've got a number of blog posts out there and white papers on various different technologies. All of those can help, point you in the right direction. Now let's touch a little bit on flexibility. Right? So virtualizing Hadoop has been something that's been pretty hot for the last couple of years, and it's getting more and more mature. Right? There are effectively three ways of doing this. The first way is native. right? This is where you actually use configuration management engines or templates, the tools that are already built into your cloud, your private cloud or virtualization platform, to be able to build up VMs that will ultimately host these roles. And that's great, but it's not really as a service, and it doesn't really leverage a lot of the capabilities of a true automated cloud framework. Then we start getting into ecosystem enhanced. Right? These are predefined templates and tools that help deliver that as a service feeling, right? Where it can be more, a little bit more elastic, and it's really custom designed to be able to run this type of workload. These are advanced templates, etc. So we see that as VMware's big data extension, used to be called Project Serengeti. That most likely is going to go through some transitions here, and a lot of those roles are going to be taken over by Cloudera Director. We also see the OpenStack data processing framework, known as Project Sahara, also does very well at this. Inside the public cloud, you can also do it in the same way of using their native images and their native VM tools, whether it's Azure Compute, Google Compute, or AWS AMIs, to actually deploy this on there. Or you can use some of their services like HD Insights on Microsoft Azure or Elastic MapReduce on AWS. When we talk about virtualizing Hadoop, it's good to separate what a good use case and a bad use case would be for virtualization. So for virtualization, we really looked at things like transient clusters. When we say transient, we mean clusters that can measure their uptime or their runtime in a matter of hours, not days, right? This is nightly batch jobs, automated scheduled jobs, ETL jobs that need to run on demand. Anytime you need to do anything massively multi-tenant, let's say you're a university or a large enterprise that had multiple divisions that all needed their own separate sets of clusters, right? It'd be very easy to manage a shared resource pool doing this under a virtualized framework. Use of excess compute, right? So maybe you don't spin up just the storage layer, you spin up only compute. Right? And so these are nodes that would attach to existing storage and really reclaim a lot of that headroom that everybody has in their virtualization farm. Maybe you need to bypass some sort of hardware limitation, memory limitation, even a warranty limitation on existing hardware. Heterogeneous hardware support. It's much easier to mix disparate hardware types inside the guise of virtualization rather than trying to do that at a bare metal layer. High elasticity, right, when you need this to expand and contract based on demand or capacity. If you're disaggregating, if you're using an alternate file system like Gluster, Ceph, or S3, SwiftStack, etc. If you're leveraging the public cloud, right? So then it can become very easy to take those same compute VMs and configuration management enabled tools and then push them into the public cloud and really start to look at the hybrid nature of public-private cloud. But at the end of the day, bare metal use cases, these are going to be things where it's a high performance cluster. More often than not, you're going to get much better performance on bare metal than you will virtualization because it's purpose built, right? Persistent clusters, clusters that have to be up, right? Whether it's for the classic 3 active archive, log ag, and data warehouse offload. High capacity clusters, your dollar per gig, is going to be far cheaper if you're using bare metal clusters than it will be if it's under virtualization. And then anytime you have to have SLAs, a job that just has to get done, right? It's best to do it on a bare metal cluster. We also start to see folks talk about the disaggregation of storage and compute. So originally, the idea was in a distributed system like this to couple storage and compute inside the same box, thus reducing the latency and round trip time every time the processor needed to go and fetch something from disk. Right? So that was the kind of the preliminary design. That has since migrated, right? And folks are adapting to new deployment patterns and design patterns where, what if I already have a large object store, a large distributed data store? Can I not just have compute off to the side of it? It makes it much more elastic, right? So you see a couple of ideas here around disaggregated storage compute. In the center column, you see on the left side, storage being provided by something that can provide object level support or NFS level support, whether it's a software solution like Scality and Ceph or a hardware solution like a Dell Compellent NAS. And then you have your compute off to the side. These are nodes that don't have a ton of disk storage in them, right? They have just enough for some local scratch space and just local working sets, but other than that, they're really just horsepower. Go over on the right-hand side, there's also the idea of if you already have a traditional Hadoop cluster and you don't need to add storage capacity, there's nothing saying you can't simply add only compute to speed up jobs, increase the resource pool, etc. for the actual processing, but not for the storage. These are all common deployment patterns that we're starting to see more and more. Now let's talk a little bit about big data as a service. So if you look on the left-hand side, you'll see this is really what a lot of large enterprises look like, where they have lots of different groups that have maybe their own sets of Hadoop clusters. Here you see one, services has their own. Maybe it's running Cloudera. R&D has their own running, maybe Hortonworks. Sales has their own. Manufacturing has their own. You get very little utilization because you've got so many different resources, so many different kingdoms of Hadoop out there. Right? What if you could shrink that? You'd reduce complexity, and you'd also reduce a tremendous amount of duplication of data. Right? That duplication of data can be a real killer, both for trying to keep things updated. Of those 4 clusters you have there running, if people are running against a customer list, which customer list? Right? At what time? Is the customer list running in services going to look different than the one in sales because they were grabbed at different times? Right? If they were working off the same repository of data, that would make it a lot easier to make sure that they're in lockstep with each other. Now you start to bring in the idea of compliance here and having less copies of compliance-related data distributed across your network. That'll make a lot of security folks and compliance officers sleep a little bit better at night. So we look at what this could look like with a solution like our Blue Data solution, which is big data as a service. You can consolidate that into a single hardware layer where you can get much higher levels of utilization, and then you can have, quote, virtual clusters that are spun up running different tools, whether it be Hadoop, distributions of Hadoop, different versions of those distributions, different tools like Spark, Cassandra, BI and analytics tools. All of those, the same group of folks can leverage them, but they have a single storage layer and a single pool of equipment. Right? This way you increase that total amount of utilization. Now, lastly, under flexibility, we have unified namespace. So the idea of a unified namespace is, going back to that idea of having something like Blue Data in there, what if you could present what looks like a single file system, but actually folders of it point to other storage systems out there, right? So maybe if you go into a particular folder, you'll see an example I drew here on the right. Under the user folder, there are some folders there that are local on the distributed Hadoop file system, but then there are stubs that point over to user data, which is actually out on an NFS store, or user IT, which is out on a Ceph store. Right? And it does this completely transparent to the users and to the underlying hardware or the underlying storage calls, right? And so you can start to leverage a lot more of your storage resources without having that needed complexity of pointing everybody to a special path and all sorts of stuff. So this is available in Blue Data. It's also available in an open source project called Alluxio. Right, which you're going to see here me talk about a little later too for some other use cases. And whether you're connecting to a remote HDFS, NFS, an S3 compatible object store, or something like Ceph, right? These are all options. Right, so how we can help? Well, for virtualizing, we've got a lot of private cloud solutions. Right, Azure Pack and the forthcoming stack will be great ways to host this. Same with any of our VMware offerings, our Red Hat OpenStack offering. If you're looking at Blue Data as a service or Big Data as a service, you can look at our Blue Data solution and white paper. And then you can come into the Customer Solutions Center and talk a little bit about this configuration and running it on Dell hardware. So there's some collateral out there. There's a white paper on Blue Data on Dell PowerEdge, as well as virtualizing Hadoop on Dell PowerEdge. And then one that we are working on writing is data tiering strategies in Hadoop. Right, that's going to cover that unified namespace piece. All right, now let's talk a little bit about resiliency. So just as with every disruptive technology, it reaches a certain level of maturity where it has to begin to take up more of the traditional enterprise workload. right? And those traditional enterprise assumptions around things like uptime, right? Once a Hadoop cluster starts to sit somewhere and starts to get used more and more and more, it becomes critical to the way the business does things. And with that criticality comes the IT oversight that has to come in there and start to harden this, right? And so the first thing we look at is backup, right? So we already know Hadoop uses software RAID to make multiple copies of every object that comes in. It's 3 total copies by default. You have your original plus 2 other copies on different nodes, but they're all in the same cluster. If that cluster's at one site and that site disappears for any reason, you've lost as many copies as you have there, no matter how many. So how do we back that data up? How do we protect that? There's really 2 principal methods. First one's going to sound really, a little bit jarring, but I promise you it's not. It's actually very, very common, and that's do nothing, right? So how did the data get into your Hadoop cluster? It was most likely sent from other systems, that those systems are most likely what are protected, and there's no need to re-protect the data at a Hadoop level, right? Since it's already protected, there's no need to create yet another source. The other method is to copy it off. So pull it out of HDFS and put it down onto a flat file system, and then you can back that up using traditional means. Right? There are also ways to back up to protected object stores through some partner technology like Coringo. And this is the classic backup calculations that you see I threw out here at the top, from a capacity sizing, data size plus your percentage rate of change and how many backups you want to retain. Right, so an example of that would be if you had 10 terabytes and it changed 25% every week and you want to keep that for a year, it's approximately 140 terabytes of backup space that you need. All right, but what happens if you don't just want to protect the data, but it's become so critical to the way you do things that it's the actual ability to extract insight from that data that matters, right? Not just the data itself. So that's when we start to look at replication. Right? Not just the ability to store data, but they also preserve the ability to query it. An offline backup doesn't cut it, since you'd have to rehydrate all that data before you could start doing anything with it. And you'd have to put that on a new cluster, new hardware. If it was your site that was lost, acquiring new hardware could take a lot of lead time. So when we look at replication, you have a number of options here. Right? If you look at pure replication, you can replicate to a smaller cluster. Right? You see in my example there, 240 terabytes. Both of those solutions are 240 terabytes, but significantly different footprints. Right? And that's because you use larger drives or slower drives, or you start to break a couple of the best practices because it's a DR site. You can even reduce the replica count. So instead of having the 3 copies of every file, maybe you've down to 2 or even down to 1. Right? Since it's a DR site, those stringent rules might be able to be relaxed. But at the end of the day, if this is something where you have SLAs that have to be preserved, the only way to really do that is to move to one-to-one, right? Move like to like. And so that the failover site, once that failover does happen, can take the same load, same capacity, and meet the same SLAs, right? Another popular thing that's often thrown in here is, how do you get the data there? You can use tools to do the copying. We'll see those here in a second. But oftentimes what we see people do is just do simultaneous ingest at both clusters, right? And maybe you have your R&D team works on the DR cluster so they don't impact production, and production is kind of preserved and holy, right? Those are some common design patterns that we're seeing. So tools that can actually do this backup and recovery. So native to Hadoop is something called DistCP, right? It's free. It just backs up HDFS, right? So you have all those other tools in the Hadoop zoo, right? Hive, Spark, all those other things. It doesn't back up that data. It simply backs up HDFS, right? It's good for batch copy. If you want something a little bit more advanced, you can look at Cloudera's backup and disaster protection, right? That's included with many of the license tiers with Cloudera, and that'll back up both HDFS and Hive. And you can see a screenshot of that on the right-hand side, where you select your source HDFS and your destination HDFS and what the file path is, and then how often you want it to replicate, all right, and whether you want to take some of the MapReduce services over, whether you want to take some of the Hive services over, etc. There are also a number of third-party tools that will do even more than this. Well, they'll do HBase replication, and they'll do migration, or even they'll do object store data protection. Right. As far as how you can get some help, well, our Cloudera solution already has backup and disaster recovery built in with all the paid tiers. Right? There are a variety of different sizes and accommodations that are made in this reference architecture to allow you to do things like dissimilar cluster sizes for replication. You can go through the Dell services, right, and have them help you do capacity planning and sizing of a backup and disaster recovery solution. And you can come into the Customer Solutions Center and talk about it with some of our subject matter experts. We're also have in draft a white paper around Hadoop backup and disaster recovery that talks about these options. All right, so now let's talk a little bit about performance, right? And a couple of hardware trends that we're starting to notice and incorporate into many of our designs. So faster storage, hands down, this one's really, really popular. Folks moving into faster drives. If you look at, the price rates of 10,000 RPM drives, we're seeing, a pretty massive adoption there. Also, the introduction of that 1.8 terabyte size has allowed more folks to start to look at it. Using SSDs, whether it's the write-intensive ones for ingest-heavy mixed use for general purpose or read-intensive for archiving. Adding in PCIe NVMe cards, that's really great to add to an existing node. So let's say you have an existing Hadoop cluster, you want to add performance to it, but you don't want to sacrifice drive slots. Well, you probably got some PCIe slots in the back. Throw one of those accelerator cards in there and use that for your to start to kick this into high gear. One thing that's really important to start talking about is that whole idea of early on in Hadoop on a 1-to-1 core to spindle ratio. Is pretty much dead and throw it out the window. And now you want to take a look and balance your total I/O. Right? With the adoption of Spark, Impala, and all sorts of other in-memory technologies, loading these things up with memory is absolutely par for the course. Gone are the days of 64 gigs or 48 gigs of RAM in your data nodes. It's pretty rare to see things leave without at least 256 gigs of RAM. Adding more cores at a higher frequency. Right, kind of the current sweet spot there is a E5 2683 V4 is really 120 watts, so it's not an insane power consumption, but it's still 16 cores at a pretty high clock rate. Also, there's some preliminary murmurings about GPUs, and this is not necessarily used in MapReduce or Hadoop itself, but rather in the Spark side and machine learning. All right, and this really makes Hadoop HPC adjacent, not necessarily sharing the same hardware, but often complementing hardware. Building an algorithm or training set and using GPUs to actually develop those algorithms, and then using Hadoop itself to crunch the data sets based off those algorithms. Right? And so the popular GPU platforms there are R730 and the C4130. Those are really the only ones that are only PowerEdge servers that are sanctioned for GPUs that have the right power harnesses, etc. We'll also see the same type of thing extend to Knight's Landing, which is an Intel Phi accelerator card, and everything else that's coming out that's imminent. Now, when we start to talk about performance, it's always important to understand bottlenecks. Right? So in an SSD, you really, it's easy to push an SSD, a set of SSDs, faster than to what a bus can handle. Right, so beware your RAID card saturation. You'll see the two diagrams off to the right. The primary difference between the two are SATA drives on the left, SAS drives on the right, and that makes a pretty tremendous difference in the bus width. Right, you see a 6 gigabit on the left, 12 gigabit on the right. Right, and then you'll see that all the way up through the stack, the PCIe controller out to the network to see where your actual network bottlenecks are. Right, so SSDs are really popular, but as soon as you get over 8 to 9 on a single RAID card, you're going to saturate it. Right, so that's why you'd start looking at some of our solutions that have split back planes with multiple perks. Also, Spark scratch space on SSD, incredibly popular. If you're running Spark on Yarn, then this is actually your MapReduce volume. Right, and so usually 1 to 2 SSDs per host outside of your HDFS for Spark is pretty popular. Also on your name node, right? There are two drives that in our reference architecture we specify as pass-through for the two types of journals. Those would be great in a large cluster or a cluster where you have a really small block size with lots of file data. Um, that would be really good to put those journal volumes on SSD. And we start to talk about tiering. So there's a couple of ways tiering is done. I'm going to cover really three common ways. The first way is having tiering occur inside your storage device. Right, so this really only works when you talk about disaggregated compute and storage. Remember what we talked about earlier about using an object store or a NAS, something like that. Well, those all have tiering mechanisms built into them, right? Data progression levels, all that type of stuff. So that can happen. Hadoop doesn't know anything about the tiering, right? It's completely disconnected from that. It's just compute spinning up a connection to an external storage device. It doesn't know. All the tiering happens completely transparent. This is popular in Isilon, ECS, um, and in some of the other object stores, right? The weakness here is there is no in-memory layer, right? So all that tiering is only at the disk side. It's only the storage side. So to do the data processing a la Spark, etc., it would still have to go fetch the data and then come back. It can't, tier from memory on out, right? So let's look at a technology that can start to do that. So inside Hadoop, since about 2.6, Hadoop 2.6 is native Hadoop tiering, right? And this is hierarchical storage management, right, built into Hadoop. It's not fully exposed in the UI, right? It requires manual XML editing, right? But it's really important you understand the way this works. This is not like traditional tiering that people might be familiar with when it comes to storage. All right, so the first thing done is on every data node, you take every drive, every storage device on that node, and you classify it as a particular type of storage, right? So you classify it as a RAM disk if it's in memory, an SSD if it's an SSD, disk if it's a spinning media, or archive if it's, say, NFS or really slow disks, right? Then inside Hadoop, right, you go in and inside the HDFS file system, you tag folders with certain storage policies. And that might be a storage policy like you see me lay out there in that table. Those are the default storage policies. Look at the all SSD one. What that is saying is that every replica of this object is going to sit on a tier of storage classified as SSD. The next one down, one SSD, means one replica sits on SSD, and then the remaining replicas sit on disk, right? And then you can see on out to the default one, which everybody's used to, is everything sits on spinning disk. It's really important to understand that this requires manually tagging directories with these storage policies, right? So that means there's no idea of automated tiering moving from hot to cold automatically, right? You would have to come in there and reclassify folders and volumes to do that. You can see an example of that deployed out here where I've done 3 tiers, a RAM disk tier, an SSD tier, and a disk tier, and then my policies can all be leveraged against that in this screenshot. But it's really important to understand there's no automated data progression this, right? That's a common misconception. So now let's talk a little bit about something that's really new. It's something that we used to know as, it's out of the Berkeley AMP camp, called Tachyon. It is now rebranded as a commercial entity in an open source project called Alluxio, right? It's an in-memory file system that also incorporates automated data tiering across 3 tiers of data: memory, SSD, and hard drive. It's got that unified namespace support we talked about earlier. It's completely open source. There's a commercial version coming soon. There'll most likely be, their model is going to be services and training or monetized, and maybe a couple of 1 or 2 premium features. That's kind of typical. It's compatible with Cloudera, native Apache, Hortonworks, Spark Standalone, Flink, and Zeppelin. I mean, you don't have to even have Hadoop to be able to use this. It's also going to be incorporated soon, on the roadmap for Blue Data. So there's a couple of ways that this can be leveraged, and I've kind of outlined 3 different options, right, on the right-hand side. The first one is one that could go into an existing Hadoop cluster today. That's where you still let Hadoop do all your persistent traditional HDFS things, those layers at the bottom, but you have really a cache space that exists as a separate file system in RAM. Maybe you put 256 gigs of RAM in these and you want to set aside 128 gigs per node for this extremely accelerated file system, right? You'll be able to copy data sets off of the traditional Hadoop into that in-memory file system and then execute lightning fast jobs against that, right? We're talking, you know, tens of times faster than anything else. This is, this is delivering a lot on the performance. Um, but at the end of the day, there's no persistence in that in-memory file system. Right? There's ways to do it a little bit, but it gets really complicated really quickly, and that's where you're going to want to engage a subject matter expert. We move on into option 2, and this is where it becomes semi-persistent. Right? So the same thing as before, where you had your persistent traditional HDFS at the bottom there, and then a layer that actually encompasses both memory and SSDs, right? And that's semi-persistent. What that means is as data gets colder and colder, it gets moved out of memory down into a persistent media like that SSD. Only that stuff moved down to that persistent tier is actually persistent. Right? So it's important to understand. You can either pass a particular flag on a file transaction to have it be written down to that tier, or you can let it sit resident in RAM only. Right? This is the idea of actual tiering. The last one is full tiering, right? Where you have that same type of semi-persistent model where RAM is the uber fast layer but no persistence, and then SSD and actual spinning disk as a data progression layer where you do get full persistency. And then you can connect out to all sorts of other storage on the back end using that unified namespace redirecting. Right? So how Dell can help? Obviously, our Cloudera solution has native tiering out of the box. You can add Alluxio with relatively minimal effort, though I encourage you to engage a subject matter expert around that. And then you can come in and talk to some of our subject matter experts at our customer solution centers throughout the US. We also have a white paper that I'm working on data tiering strategies for Hadoop that'll cover a little bit more of this in detail, and look for that sometime in the future. The next thing I want to touch on is an idea around a proposed next generation stack. Right? So this would be incorporating all the stuff we've been talking about today. Right? So we start out at the hardware private cloud layer, right, with your infrastructure. How you get that infrastructure, it will vary use case to use case, but that's your bare metal hardware or your private cloud VMs. We're running Linux OS. None of this is new. Most popular right now, Red Hat CentOS, Red Hat and Red Hat derivatives. You have an optional big data as a service layer, right? And then you have your Hadoop distribution or Hadoop distributions, if this is big data as a service, sitting at the next layer. Right? Then you have your performance tiers. Right? You're either a caching layer delivered through Alluxio or a persistent storage layer delivered through the native tiering. Then you have HDFS and then MapReduce and Spark on up before you get to your customer access and tooling layer at the very top. Right? So this is the incorporation of a big data as a service layer and then the two tiering layers. That's really the new stuff here. What does this look like from a hardware perspective? Right? So again, this is just a conceived idea, but it's something that we're seeing go out in designs for a number of customers. If you want it converged, in other words, standard compute storage inside the same box, this is that's delivers on all those promises of linear scalability. This really caters to those next generation workloads that are Spark heavy, in-memory heavy, balances still capacity with that performance. Right? So this is built on our 730XD. This is the model that has 16 large form factor and 2 flex bay, so it's got that 4-drive mid bay. You've got a capacity tier, which is all your classic spinning drives. Right? These are 4 terabyte drives. You really don't want to go much bigger than that because that creates a pretty big failure domain. Though in certain use cases with full knowledge, you could. Performance tier, some write-intensive SSDs. All right, one for your actual performance tier and the other for Spark scratch space. Right? Then we're going with dual 10 gig Intel NICs, and really we're probably going to start to see this go up to actual 40 gig NICs. So remember, that's 2 10 gig dual port NICs. That's 40 gigs actually leaving this chassis. Right? That's not 2 10 gigs. as we start to see it, kind of get adopted more, you'll see native 40 gig adapters there, or even 100 gig adapters, as we start to see that pop up more and more. A lot of RAM, 512 gigs, especially if you're going to incorporate things like Alexio. You're going to lose any of that space that you give to Alexio. You're going to lose that as addressable RAM space. Right, so if you gave a 256 gig in memory tier, then that would only leave you 256 gigs left over to do all your data processing and all your normal OS stuff. And then some pretty beefy CPUs. Right? Now you'll want to watch on the CPUs to make sure it's a kind of CPU that's compatible with this type of chassis. With so many drives in there, there's some thermal issues, and you work with your specialists to actually get you the right compatible chip. Now, what about disaggregated? Right, so this is the unified converged chassis with compute and storage in the same box. But let's take that over to, disaggregated. This is an easy way. This is something that we've tested here in the Solution Center, and is definitely a very, very, very solid option. You have your storage layer provided by boxes that look, very similar to our R730XDs. You can also start to look at some of our other solutions around the DSS Dell Scalable solutions, 7000, 2500s. Pretty reserved configs here. A couple of 10 gig NICs, low end CPU and memory. You don't need much memory at all. If this is only providing your storage layer, remember, no compute whatsoever, no Alexio, no in-memory, no Spark. This is just compute. You could get by with 32 gigs of RAM in these guys, most likely. As far as software that this is running, you could use Hadoop's HDFS, maybe licensed or unlicensed, depending on your use. Ceph object storage, OpenStack S3 compatible Swift, Gluster, or even EMC's ECS. And we have our compute layer. Right? This is where actually all the work's done. So the hardware here could be any of our compute chassis. Anything we can put processors in it, that's what you want. You're going to want a little bit of storage for OS and scratch space, right? And if you're going to do tiering, Alexio tiering, etc., you might want to look at some different options there. This can even be VMs, right? This is just raw compute capabilities with network and scratch space, right? So these are just the tip of the iceberg as far as options. So that concludes the summer 2016 trends. If you have any questions at all, please don't hesitate to reach out to one of your subject matter experts or us at the Customer Solution Center. Thank you.